All right, this is the last topic we're going to cover, eigenvalues and eigenvectors. And before continuing on this video, if you haven't already watched the first 6 minutes of this 3 blue 1 brown video, definitely go back and watch it. This video does a really good job of explaining visually what eigenvalues and eigenvectors are. So I highly recommend watching that. But let's look at definitions. Given a square matrix A, an eigenvalue-eigenvector pair is a non-zero vector x and a scalar lambda that satisfy this equation. So with this, x is the eigenvector, and lambda is the eigenvalue. Now a matrix usually has more than one eigenvalue, and each eigenvalue has some eigenvectors that go along with it. If you think about what this says that if you multiply the matrix times the vector times the eigenvector, what you get is just a multiple of it, multiple of that vector. So let's look at an example down here. This example says, verify that this and this form an eigenvalue-eigenvector pair for this matrix. So to verify that, we've got to multiply a times x, and we've also got to multiply lambda times x. And we should get the same answer. So let's write those down here. Over here we get 1652 times 6 negative 5. And over here we get negative 4 times 6 negative 5. And one of these is obviously easier to do. You multiply, if we multiply this out over here, it's just scalar multiplication. So 6 times 4 is 24. 4 times 5 is 20. And so we get that. And this kind of gives us the first sort of reason that eigenvalues and eigenvectors are important. If you have an eigenvalue and an eigenvector, then you can do matrix multiplication by just doing scalar multiplication. But let's come back over here and verify that this is correct. So if I multiply this times that, I get, let's see, that's going to be 6 minus 30. And if I do the bottom, this times that, I get 30 minus 10. So I get negative 24 and then positive 20. These are equal, so that verifies that this is an eigenvalue and an eigenvector pair. All right, let's look at one more thing here. Verify that these two things are eigenvectors of this matrix, and then find the eigenvalues that go with them. All right, so what we've got to do is multiply this matrix times this, negative 3. I'll tell you what, let's do the other one first. 1, 0, 0. Because that one's going to be really easy to do. When you multiply this out, let's see, we take the top times this. That just gives us the top number. So it gives us 1. Then when we multiply the next row times that, basically it's just going to copy that first column. So we're going to get 1, 0, 0. Now we're saying, is this a multiple of this? Yes. So this is an eigenvector, and the eigenvalue that goes with it is 1, because multiplying that matrix times this is equivalent to multiplying this times 1. All right, let's do the other one. All right, if we take this, multiply it by negative 3, negative 1, 1, what do we get? Well, let's see, this top row, we get negative 3 plus 2 plus 1, so that's 0. The next row, we also get 0. And the bottom row, we get 0 minus 1 plus 1, which is 0. So the question is this a multiple of this? Yeah, and it's just a zero vector, but it's the we've multiplied by 0. So the eigenvalue here is 0. All right. So anyway, that's just a couple of sort of starter examples where we're verifying that something is an eigenvalue and eigenvector. What we're going to look at next is geometric interpretation, and then we're going to work our way through finding, given a matrix, finding its eigenvalues and eigenvectors. But we'll stop this video here.